So now we're going to talk about the addition method. Sometimes this is called the elimination method, depending on what textbook you're looking at. But to go over the basic idea and what's allowed here and what's okay, is to say if I had A equals B and I had C equals D, then if I said A plus C equals B plus D, that would be a true equation. And this all comes about from the addition property of equality. The addition property of equality is the property that says if we know that A equals B, then I can add C to both sides. That's legal. But with what we learned about substitution, C and D are identical, they're equal. So I could replace this C with a D, and that's okay. Now, what we're looking at here with the A's, B's, C's, and D's isn't helpful, but it's legal. What becomes helpful is if we think back to what worked in substitution. What worked in substitution was to take an equation that had two variables in it and come up with a way to rewrite it so that one of the variables went away. And we only had one variable left that we could then solve for. So the idea of the addition method is that we only want to do it if when we add them together, one of our variables goes away. And so this first example I've called the perfect setup. Because if we add these two equations together, and by adding them together, I mean let's add the left sides together and add the right sides together. 7x plus 8x is 15x. But the important thing is that negative 5y plus 5y is 0. So that's what I mean by it's going to go away. 5y minus 5y is 0. There's no more y's. And 54 minus 24 is 30. So if the y's go away, I'm left with an equation that only has x in it, and I can solve that. If I divide both sides by 15, I get x is 2. Now to find out my y value, I do need to plug it back in, and it's a little more complicated than the substitution method because we are going to have to do a little bit of algebra. It doesn't matter which one we plug it back into, but when we plug it back in, we're going to get 8 times 2 plus 5y is negative 24. So 16 plus 5y is negative 24. If we subtract the 16 to the other side, we get negative 40. Divide by the 5, and we get negative 8. So we find the ordered pair 2, negative 8 is the solution to this system. And we can always plug it back into both equations to double check. But what I want you to notice here is the fact that the 5 y's were opposites of one another was the key. So when we add them together, the y's went away. So this problem here isn't a perfect setup, but we only have to do something to one of the equations. So what we can do with an equation is we can multiply both sides of that equation by any number we want that's not 0. So as we look at these, I want to say, could I multiply one of the equations by something so that the coefficients matched up? And it looks like if I multiplied this first equation by 3, then the y's would match up. They'd both be 15. We'd have a 15y in the first equation and in the second. But it's not quite right yet because they'd both be negative 15y's. If we add together negative 15y and negative 15y, we get negative 30y. And we wanted the y's to go away. So what we're actually going to do then is multiply by negative 3. And if we do that, we want to rewrite the entire system. We're going to end up getting positive 9x plus 15y equals positive 126. And then we're going to rewrite that original second equation directly underneath here. And now we can add these two equations together for the addition method because of the fact that we have one of the variables being opposites of one another. And so now 9x minus 2x is 7x. 15y minus 15y is 0. And 126 minus 98 is 28. And once we get to this point, it's pretty easy to just divide by 7 and get x equals 4. Now, as far as where we plug this back in, we can plug it back up anywhere above here. Our goal is to solve for y. So wherever we want to plug it back in to solve for y, we can. Now, I'm going to go ahead and plug it back in the original, but we could have plugged it in to the second equation. We could have even plugged it into our modified equation, because the modified equation was still true. We had multiplied both sides of the equation by a value. That doesn't change whether it's true or not. It's still a good equation. But I'm going to plug back into the first, and we get negative 3 times 4 minus 5y is negative 42. And so now we can do that arithmetic. We can add 12 to each side, and then divide by negative 5. This gets us the ordered pair 4, 6, and that's the solution to this system. So for our third example here, we're going to look at a system where I can't simply multiply by one of the equations. Not in a neat, nice, easy way anyhow. If I wanted the x's to match up, I'd have to multiply the second one by 2.5. I could do that, but that gets kind of weird. If I wanted the y's to match up, I'd have to multiply by 1.5. That's kind of weird. So instead what I can do here is I can find a common number that I could bring both of them up to. I'm looking for a number that would be a multiple of both coefficients. So I'm really looking for the least common multiple between the coefficients. So if I want to look at the x's, the least common multiple would be 10. If I want to look at the y's, the least common multiple would be 6. Now in this problem, I would probably want to eliminate the y's because they're already opposite signs of one another. So I don't need to multiply by any negatives, which is going to help to make sure I don't make as many sign mistakes. So that's what I would notice here. And so I need to build them up to a 6 each, which means the first equation I need to multiply by 2. In the second equation, I need to multiply by 3, and that will build both of the y's up to a 6. So let's go ahead and see what this system becomes. As I distribute the 2, I get negative 10x minus 6y equals negative 2. And as I distribute the 3 across the second equation, I get negative 6x plus 6y equals 18. Now, since the y coefficients are opposite, I'm ready to use the addition method. I can add these together to get negative 16x equals 16. And so x is negative 1. I can then take that value of negative 1 and plug it back up into any equation I want. So I have negative 2 times negative 1 plus 2y equals 6. Negative 2 times negative 1 is positive 2. I can subtract 2 from each side and then divide by 2. And now I get the solution, negative 1, 2. Now this is the last example from your notes. I want to give you a little bonus here though, because if you go back to our lesson on the substitution method, we had this super ugly problem here where we had these crazy answers. And I had told you at that point with those crazy answers that there was a better way of doing it and that the addition method would make it easier. And I just want to point that out here. So I rewrote our modified version without the original fractions in it. So we'd clear the fractions no matter what. But I want to point out how we'd approach this problem now. So we could go ahead and modify the y's since they're opposites already. And so we could multiply the first equation by 4 and the second one by 7. And let's see where that takes us. The first equation becomes 12x plus 28y equals 84. And the second equation becomes 63x minus 28y equals, I'm going to use a calculator off to the side here, 252. Our numbers are big, but they're not fraction big. We add together to get 75x equals 336. Now if we put this into our calculator, it's going to reduce the fraction because both are divisible by 3. And we're going to get 112 over 25, which is what we got after a ton of crazy work and distribution and combining like terms with the substitution method. Now we could plug this back in to solve for the y, but I want to show you another kind of trick here. Instead of doing that and dealing with the fractions, we could just go back to the original and say, when I eliminated the y's, I was able to solve for the x. So why not eliminate the x's and solve for the y? I could do that if I multiplied this first equation by -3, because that would make my x's opposites. I would get -9x minus 21y equals -63. In the second equation, I'm going to copy down. So when I add these together, I get -25y equals -27. And if I divide by the -25, I get 27/25. And so I get this exact same super crazy answer without all the crazy work. This work really wasn't too bad. We never got fractions until really the last step. We got bigger numbers, but it wasn't too bad. So that shows you the motivation behind using the addition method as opposed to the substitution method when you're going to end up getting some crazy fractions.